Hello, everyone. Good afternoon. My name is Tai, and I'm an engineering manager at Datadog. In my past experience, I used to be a backend engineer, and I love all the concepts of scalability, reliability, and resilience. And that's why I'm stick to this field of work. So today's talk is named Coping with Reality, Chaos Engineering in Action, where I will revisit how we get to the complexity that we have today, and also explain how chaos engineering as a practice can help us understand our system a lot better and prepare for outages should they happen in production. Here is the agenda for today. First, after a very quick introduction, I will explain to you why in our company we do an AZ loss game day every quarter. And after that, I will need to bring us back to some of the basic questions to get us to explain how we get to the complexity we have today. Next, hopefully the most compelling part of today's presentation, chaos engineering and game days. Finally, I will need to recap about our reality and the associated challenges that we have. Now, what if I tell you that every quarter we purposefully bring down an AZ? Just to level set, an AZ is a geographically isolation concept. For example, your company may have some customers in Los Angeles. You put a data center there. You may have customers in London, so you put another data center in London. The purpose of the game day is to see how teams in Datadog react when an AZ is purposefully brought down. We want to see if teams can communicate, coordinate with each other effectively to mitigate the loss of an AZ. The key takeaway here is that it's not enough just for your service to survive. You have to survive as an organization together. And by surviving together, I mean that your shared library, your shared toolings, your configuration, your infrastructure have to survive together as well. And the only way for us to improve is to take iterations of game day, simulated outages. So this is all not too hard to achieve. For example, in any large-scale systems, we have a concept of load balancer. And in Datadog case, we have a fabric where DNS is resolved. And we are aware of which AZ is having some impact. And we can effectively reroute the traffic from the impacted zone into the healthiest one. But it's not that simple. What happens exactly? During our first iteration, every alert from all the components, even customer-facing to the backend, went into alert, and it caused panic for everyone on the call. And it doesn't help anyone because all the issues happen at once, actually managed to cover up the real root cause. So after the first few iterations, we managed to get better. We fine-tune our alert just to discover that when the impacted zone goes down, the elevated traffic to the healthy zones are actually kicked in too fast, and our auto-scaling couldn't cope. And therefore, it caused brownouts in the backend, and it cascades the errors across components. Of course, we fixed that, and then we discover even trickier issues with database. Because of the fact that we bring down an AZ, effectively, we remove the nodes and the pods in our infra, and our database cannot elect a new leader, and we run into a situation that we cannot replicate data, and that causes a risk that we may lose valuable customer data. So I have talked about alert fatigue, elevated errors, slow auto-scaling, and database quorum loss. Of course, I can go on about different non-obvious issues like this, but why exactly are we talking about these points? So some of the lessons that I noticed are redundancy is very different from resilience. Just because you have redundancy doesn't guarantee that you will survive the AZ loss. And failures at this scale are already happening in production. And unfortunately, engineers are just not used to it because we don't see it day to day. And incidents usually, large or small incidents, reveal bottleneck in our coordination. And runbooks usually cannot catch up with these edge cases. And finally, our systems are just too complex to reason about. So I hope that was a compelling opening. And now we need to all take a step back to understand why we got to a situation that we have today. So this is a very comforting diagram aligning any architecture diagram. So whenever we join a new team or a new company, this is something that we usually do first. We go to the whiteboard, we try to sketch an architecture diagram. In Datadog case, our clients are usually the box on the left. Always try to establish connections to Datadog server. Our customers expect that if they send telemetry to Datadog, we can keep them, never lose them. And later on, if they query the data, we can always display visualization for their metrics and so on. So in this case, we have an intake, which is usually the most customer-facing component. We never allow to lose data. So that's why we introduced the distributed queue to make sure that all requests are being queued correctly. Somewhere in the distributed systems components, we introduce a cache layer so that we can serve requests faster and more effectively. What I mean is all of this are still very comprehensive, very easy to understand, but the real production environment are usually looking like this. There are usually thousands of microservices constantly interacting with each other. And just by looking very quickly, you can notice that there are some hubs where the remaining services trying to establish connection to. If errors ever happened in these hub of communication, you are likely to have a high severity outage in your production environment. Back to my original point, I wouldn't try to draw this on a whiteboard because it is too hard for anyone to explain what is going on. It is very hard for any new engineers to understand the finer details of all of these interconnectivity. And with that complexity, we also have the associated problems. So with this slide, I'm trying to emphasize one point, that is, system failures are inevitable. Systems that can fail will fail. Humans sometimes make mistakes. Even build systems, deployment systems, mistakes will happen. Even very large and famous cloud providers occasionally have outages that cause cascading impacts on customers' production environment. So in case if it's still not clear to all of us, I think the impact is already quite prominent if we don't care enough about these types of systemic failures. In terms of communication, we spend a lot of time not knowing what kind of the right questions to ask during incidents, and it wastes the time to mitigate the issues. In terms of collaborations, because different teams will have different methodology, different assumptions, or if we reach out to a wrong team during an incident, it may not work. It causes a lot of friction. Coordination, obviously, when the time is critical for everyone to sit down together, explain, or finding the mitigation, we instead trying to clarify this is not our ownership area, and ramping up onboarding time. Obviously, more complexity means more delays when we try to onboard a new person, and this has a direct negative impact on our business growth. I have a picture of a nice lecture hall here with valuable lessons on the whiteboard, but unfortunately, no students care enough to show up. This is very similar to our situation here. Valuable lessons from productions are at risk of being wasted because the way organizations work is that teams are often working in their own area of expertise. When incidents happen, these teams are usually at the forefront, being dispatched to solve incidents, to find mitigation, or to extract valuable learnings from post-mortem. The subtle problem here is that even those learnings are scoped within the team's understanding of the issues, and it doesn't necessarily have the holistic view. A small problem that a team is facing can be an early indicator of a wider organizational problem that organization isn't even aware about. Fragmentation in terms of how we dispatch teams to solve incidents make it harder for the organization to realize any patterns and to have a good strategy to tackle those issues going forward. So Instead of waiting for such outage to happen, engineering teams and organizations can take a first step, simulating the errors, dispatching engineering teams to make sure that they know what to do when such outage at that scale happens, and they train the incident response muscle ahead of time. Which brings me to the most interesting point of today's talk, which is about chaos engineering as a practice. A textbook definition of this practice is about doing failure injection, usually in production environment, to spot the weakness of the system before it happens and impacting customers. So why would anyone want to do this? Would anyone want to try to answer? Is there a good reason for engineers to do chaos engineering? Injecting failures in productions? Anyone? Yes, please. Make sure your process actually works. That's a good one. Maybe you are an engineer who is curious enough about the way your systems react in abnormal conditions. Or maybe you are a manager who has to deal with compliance, who needs to show compliance engineers that your systems actually are AZ resilient. Maybe you need to show additional evidence during audit seasons. Or maybe you are just a normal engineer who don't want to be paged at 2 a.m. and who wants to practice incident response during the normal working hours. I have another photo slide. This image represents a typical hustle bustle of a city, and more exactly, it depicts a busy, chaotic traffic jam. To me, this is a perfect metaphor for what chaos engineering can bring to us as a practice. We have a few elements that worth discussing here. First of all, we have high amount of traffic. The density of different transport, different vehicles are trying to cross the road represents the number of complexity, the number of interconnectivity in microservices. We have unpredictability at the junction point, just like how these vehicles have to coordinate with each other very carefully to avoid accidents. Components in microservice architecture needs to adhere to API contract so that we don't have a cascading 503 errors, for example. We can have retriable errors. We can have clients retry on certain amount of errors. The third element of this photo is the high dynamic of this movement. It suggests that even when traffic jam happens, when critical condition happens, the impacted service needs to have the ability to absorb a partial amount of failures and ideally be able to recover gracefully after a certain amount of time. Hopefully after 5 minutes or after half an hour. So this image, although it looks a bit chaotic, it has a certain orderly nature in it, which suggests the exact kind of activities that chaos engineering will do in our events. The goal of chaos engineering, obviously, or not obviously, is not to make this traffic junction disappear, but instead to make sure that all participants are prepared. They know that these situations, although critical, are normal, and it will happen nonetheless. And during such high-stake events, people are ready, have the trust that eventually things will be all right. So with that in mind, I want to talk a bit about solution implementation. And in this case, we have an open source solution, Chaos Controller. It is actually the way Datadog engineers inject failures across our components. This is built with Kubernetes, with the assumption that engineers use Kubernetes. It has a few philosophies in mind. First, it has to be fast and operational at scale. The goal is to be able to inject failures, not one by one, but by thousands of targets in a matter of minutes. It has to be very safe, and even in the environment that is highly disrupted, it has to continue to be safe and operational. Any engineers, if they start discovering that something starts to go wrong, they should have the ability to terminate the failure injection at any point in time. It has to stay simple. Any engineer just spend a few minutes reading the configuration should understand very clearly what this disruption is going to do. And it has to be operational at low cost. For example, your teams, if you don't have time to do chaos engineering, it shouldn't cost your infrastructure any additional penny. So this is a YAML file. YAML, because most of our internal infrastructure already use YAML, so we want to reuse as much as possible. So this file basically describes a disruption that will inject the latency spike failure scenario in. So this configuration actually takes down an internet connection, so it drops 100% of network, outgoing network, and it targeting the app called Demoker. So originally, you will see that this Demoker app can constantly contact Google for additional information, but after injecting this failures, this disruption, things will stop being able to reach out to the internet. So the chaos controller has been used for a few years, 3 to 4 years in Datadog with high success. But the next step is to make it very simple for any new engineers that join the company to be able to launch a disruption as easily as possible. I want to take a moment to clarify what I mean by disruption and failure scenario. So what is a failure scenario? Failure scenario is a scenario, basically. You say that your system will react in this way when some abnormal condition happens. So that is a failure scenario. A disruption is when we launch the failure scenarios targeting a Kubernetes namespace, pod, or node. So that is our terminology of disruption. A one-click disruption is the ability to pre-author the configuration here. We have the configuration or our failure scenarios that always targeted a service under test. And on our UI, any engineers can start a disruption with a matter of a few or one click. So we developed the concept of steady state hypothesis to encourage engineers to document what their expectation about the steady state of their service. So you can see that we try to associate the hypothesis with all the failure scenarios. In this case, engineers can send us the monitors that they are interested in monitoring during a disruption. If things start to go differently, we will send a message to their Steam Slack channel to ask them if we should proceed. Or at the end of the exercise, at the end of the disruption, we will tell them that basically their hypothesis has been violated and they should think again about their steady state. And of course, it doesn't need to just be a simple monitors. Engineers can provide composite aggregated monitors, which will look at across their different areas of their systems. If they use Datadog, they know that they can send us the amount of logs error so that we can let them know when things start to change. Disruption cron. This is a logical next step for us because we want engineers to have the ability to not only launch disruption once, but it should live very close to their SDLC. So if they can schedule a disruption cron during near to some of their deployments, effectively they have the ability to validate against regression. Okay, one of the more advanced application of chaos engineering is doing game days. Contrary to its name, which may suggest gamification, something relaxing, game day is actually a very high-stake, sometimes nerve-wracking event. Usually it involves more than one team, and it has the following characteristics. It has to have the intentional exploration. Different teams need to agree with each other that they have clear objectives, where to launch the game day, where to launch all the disruptions in the game day against, and they need to agree that they will spend time to effectively learn about how the systems react in abnormal conditions. So this is an oversimplifying graph of how the game day process looks like in most organizations. So if you have never done any game day, any chaos engineering before, you probably don't have a good idea of how your mental model will match your reality. So this is where we usually suggest the service owners to sit down, to outline some of the expectation, the hypothesis, and to run the first game days. It is very likely that they will discover the discrepancy between their mental model and the reality. This is where we push them to write postmortems and define some of the action items. Usually these action items span across multiple teams. And the next step is to make sure that every team follow up accordingly. So you have a situation where you manage to fix the cross-teams errors, or not errors, but situations, circumstances that is not ideal, and then you rinse and repeat. You propose a next iteration of game days. Hopefully you discover more discrepancies and more postmortems, more action items. So I want to talk about our internal solutions for this. So Game Day platform was built with the intention to reduce the operational requirement for participants to perform game days. It is very easy to use, and it has a strong emphasis on coordination. We know that it is very hard to schedule time for all the participants to get online, get on a virtual call together, so we want to improve that. We want to make sure that game day is an iterative process. It shouldn't be a one-off where you do a game day before your service is launched in production, but it has to stay iteratively. And we try to improve our automation as well to reduce the toil, especially when we need to schedule and invite people to participate. What I have on screen here is one of the ways we use the Game Day platform to schedule a game day. We have a tight integration with Google Calendar, and based on the workday information of employees in the company, we are able to map the service and team's relationship to the person who will represent that team and service during a game day. We send them an invite on Google Calendar, and we also have a sync bot that makes sure that all the response on Google Calendar got synced onto this screen. The live execution view is something that we are very proud of because we know it was very hard to get people attention for a number of hours during a game day. So we completely transformed large-scale game day with this view. The website not only shows live progress, but it also allows us to distribute different workflows to different teams. And each of the workflow will eventually end up being a Slack channel, so that team has a dedicated space to work on different issues that we discovered during a game day. This view not only increases the visibility of a game day, it improves the coordination aspect because maybe not at all the time during an event, we need all the teams involved to be active. When we discover some issues that are relevant to that teams, we can ask them to show us the latest updates or join the Zoom call when necessarily. So pre-flight checks is one of the heavy user requests that we receive because for some activities that may be costly for some teams, like a game day, they want to have a pre-event meeting where they go through all the setup verification before the game day actually starts. So we actually support this, and we send a reminder for the game day organizer ahead of time if one of these pre-flight checks hasn't been checked. Okay, to recap, game day is a very important concept. Just like this image of intricate network layers, where one lane things are moving very swiftly as normal, one small errors in the other lane can grind things to a halt, and you don't want that in your distributed systems. By doing game days, you will discover all the possible failure paths that your service may encounter, and you will have a built-in preparation when bad things like this traffic jam happens. Now we move to the reality reflection part of today's presentation. This is the reality. Although I really want all engineers to know about service scalability, reliability, and resilience, it's factual that not all engineers are equipped with these knowledge. The logical question is, how do we turn these non-expert into expert? For me, we should reduce the initial learning curve to practice chaos engineering, and we should target the first few iterations, the first few exercises to the things that the service owners know best, usually their services. And by that, I mean we should start small and build gradual confidence. We can pick something that is as simple as a host failure or a latency spike. A little bit more advanced one is a dependency loss failure scenarios, CPU or memory utilization spike to see how dependency react when this happens in one of the dependency. And one of the most advanced one is actually zonal degradation, which is the stuff that we started this presentation. I attached the configuration of this on the right-hand side of the presentation. The point here is more like to show you that we actually do this quarterly in our company. And why? The reason is we never know to what extent a degradation in a zone will happen. But if we manage to evacuate from that zone, effectively it's like a reset button. You don't need to care about what is wrong in that zone at the moment. You evacuate, and half an hour later, when the status page of that cloud provider comes back normally, you resume connection to that impacted AZ. It will simplify a lot of unknown issues in AZ because we already have the simplifier tested solution. Right. The last photo here is the allegory of the cave by Plato. And in this image, we have people mistaken their shadow on the wall as reality. This is exceptionally similar to the way we think that we understand how systems work in production. The fact is there is always gaps in our mental model and reality. And we need to change our mental model in a way that we welcome changes, we welcome unknown, and chaos engineering, game days is one of the ways to encourage us to think and validate our thinking. And with that, that's the end of my presentation. Thank you for listening.
Thank you very much, Tai, for this interesting talk. Are there questions from the audience? Back there, Mark?
Yes.
I just need to put the other mic down, just a second.
Oh.
So thank you, Tai, for this very interesting talk. I find it a very interesting topic and an important topic. So I've got two questions for you. The first one, at Datadog, how difficult was it to introduce like this work culture where you're doing chaos engineering? Because a lot of people are afraid of willingly taking down any type of service or introduce some sort of chaos. And the second question, if I understood correctly on your game days, this date is announced, so they actually know something gonna happen, but they do not know what?
So I will answer the questions one by one first. So was it easy to convince engineers in Datadog to do game day? So the answer is somewhere between the hard and easy spectrum. There were some challenges in the first place on especially why we need to do this. Am I already not busy enough? Why do you ask me to do additional things? And this is basically a trust question, and it is not exactly technical, but it has a degree of people management as well. We need to build the position in the company such as, for example, SRE is there to make sure that all engineers focus is enough, not only on the happy part, but the failure part as well. So it started with the SRE culture, and then we were able to convince people that this is the right stuff to do, instead of perceiving us as some monkeys that are trying to ask them for additional work. So this is an ongoing effort. If we do something not good enough or not clear enough, people will not always trust us. So this is one of the reasons we try to make sure that we make use, the most use of people's time. Can you remind me of the second question?
The second question was about the game day.
Okay.
So you're sending in a calendar invite,
Yep.
so they know at this day something gonna happen,
Yes.
but they do not know what.
So that is actually my eventual vision, to be able to do game day in a stealth mode. So people should not know the specifics. They just need to trust me enough that during that day I will do something, and that service ideally, if everything is built properly, they shouldn't fear that. A lot of game days, if not all of the game days in Datadog now, is still something more like a stage event. So I still need to encourage the game day organizers to explain and think in details about what they are going to do, what kind of blast radius it's going to have. So it still feels like a stage where I encourage people to think deeply. Ideally, I shouldn't need to do that.
Any further questions? If not, another question here, maybe.
So I think you mentioned people can disable the chaos engineering if they want to quickly recover, right? So you have an opt-out, like let's say, okay, I can't figure it out right now, we're busy, let's just get the system back up and running.
Yeah.
Did you have issues where people sort of abuse that and say, you know what, I don't feel like it today, let's just get it back up and running, and they just keep doing that and they never play the game?
So no, but I acknowledge the possibility of people will abuse the emergency stop game day because they have plenty of reasons they can fear about the systems. I guess we are lucky enough at the moment. Our problems now is to get more adoption, more people to organize game day first. Maybe eventually, if it becomes a top-down priority, people can feel that they don't need to do this, then that problem may surface. But at the moment, it is not a problem. Thanks for the question.
Cool. Any more questions? If not, let's thank Tai again for his interesting talk.
Thanks a lot.